Hi, I'm Yejin from University of Texas. I'm an assistant professor of School of Biomedical Informatics. So the presentation title is a little bit changes. So today my talks will be about some reinforcement learning for Parkinson disease. So this work was done with my collaborator, Dr. Jessica Suxkan, Dr. Brian Shields, and Dr. Xiaochen Jiang. So this work is still under review. We submitted to the JAMA Health Informatics. So Parkinson disease. Parkinson disease is a progressive and chronic neurodegenerative disease. This is the second most common neurodegenerative disease, just only after Alzheimer's disease. And the US annual economic burden for Parkinson's disease is estimated at like 52 billion. And the main symptoms of motor dysfunction, the main symptom is motor dysfunctions like resting tremor, resting tremor, and some posture instability or rigidity of muscle or slowed movement. Unfortunately, there's no medication that slows or stops the progressions of Parkinson's disease, but there are some medications that might help relieve your symptoms and improve your quality of life. And the most representative medications are levodopa, dopamine agonists, and MAO-B inhibitors. But there are some challenges in pharmacological therapy. Actually, decision-making in medication combination is not straightforward, as the PD is very complex and heterogeneous disorder, and there's a number of factors to consider at a time, such as ages or motor functionality or past drug responses. And what is worse, 32% of PD patients receive only primary care without neurologist care. And in this case, this challenging medication combination is getting worse even more. So actually, there are some medication guidelines like this. This medication guidelines suggest taking some levodopa or dopamine agonists, depending on patient functional disability, and sometimes suggest the combinations of therapy. But this clinical guideline lacks a lot of detail, and it doesn't fully reflect the true complicated natures of Parkinson's disease. So here, we'd like to improve this medication guideline using reinforcement learning. So reinforcement learning is just the third branches of machine learning. So there's a supervised learning and unsupervised learning, and then reinforcement learning. We use reinforcement learning to derive the optimal sequential decision-making model, such as Markov decision model. And the most famous successful story of reinforcement learning would be AlphaGo from the Google DeepMind. For example, let's see this example. The AlphaGo, so the decision-making model, this Markov decision-making model consists of the virtual agents, and there's an environment that interact with these virtual agents, and there's a state and actions. So in this example, the AlphaGo will observe the current state of game, like this is the game Go, and then make actions based on this current state of the game. So here, AlphaGo decides to put white stones over here, and the environment would be here. It would be the human Go player, Lisedo. So Lisedo interact with AlphaGo's actions and put another stones over here. And the state will be updated. The AlphaGo should reflect these updated states and make another actions accordingly. So this AlphaGo repeats this process until end of the game. And at the end of the game, the AlphaGo gets rewards if win and get penalty if lose. So as you can see here in this example, the reinforcement learning is just nothing but to determine how to act to maximize the reward. To do so, virtual agents learns about the world by interacting with it as a trial and error, and it maintains or improves the estimate of the value of taking an action from a given state. So we'd like to formulate our medication process as a sequential decision-making model. So the virtual agent here will be clinicians, not AlphaGo. So disease states will be the patient's models based on the patient's current status. So clinicians observe patient's current status and make actions, make decisions, what would be the best combinations of medication. So clinicians orders medication, and patient take the medication, and that medication works with patient's motor symptoms, and patient motor symptoms will be updated accordingly. And then clinicians observe this updated patient status again, and make another decisions accordingly. So the question we'd like to solve is what is the optimal combinations of drug as disease progresses? And our objective is to derive PD medication regimen for the best combination at current disease states using reinforcement learning. So the data we have looks like this. So we have around 400 of drug-naive and early-stage PD patient. And each patient is represented as a trajectory of states, actions, and reward. So state, actions, and reward at each visit. So here, the state will be the patient's current disease state. Like this patient's disease state will be defined as a combination of like the functional disability or previous motor symptom score or other cognitive score and many other variables. And the action will be the medication that the doctor, the physicians ordered. So we focus on the 3 types of medication, levodopa, dopamine agonist, and others, such as MAO-B inhibitor. And there's 8 combinations of medication from no medication at all here to all medication at a time, like all 3 medication at a time. So this is the current patient status. So the physician given medications over here, and there will be a reward. So reward will be here is a motor symptom. Actually, it's a negative reward, a penalty. So we'd like to minimize this reward, these motor symptoms as much as possible. And we also consider the number of medications as a penalty because we'd like to avoid drug overuse. So our objective is when there's a new patient comes in, we'd like to infer the disease states over here. And we'd like to suggest good actions. And there will be a reward. And after, when the patient is visiting again, we'd like to infer the states and actions and rewards again. So the method is straightforward, actually. So we first define the disease states. So we first identify the main disability of the motor functions, whether this is a kinetic rigid or tremor dominant or a mixed type of them, and derive separate disease state. The reason being here is that we'd like to incorporate the prior knowledge as much as possible. So the existing medication guideline usually separates this disease state at the first stages. So we'd like to mimic the same actions of the existing clinical guideline. And then we learn a regression model, and the regression model is actually to predict the UPDR score, which is the motor symptom score for the next stages using the current variable and the next actions. So we use this estimated severity score to partition the disease states. The variable we use is following here, like some severity score of the current disease states and the ages and cognitive scores and many other variables. So once we get this disease state definitions, we formulate this one as a Markov decision process. So once we have definitions of the disease states, then the afterward is very straightforward. So we use a policy iteration to optimize the medication regimens. So we first derive the transition probability of certain state to the next states from the data. And then we estimate the value of a certain states. So value of the certain state will be computed as expected and cumulative sum of this one. So this is all the value when you make a transition from current state S to the next state S prime. And we also extract clinicians' policy from the data. Here we didn't assume any transition probability, any transition assumptions over here. We just extract the clinicians' actions as much as possible, close as much as possible. So yeah, this is our method, and this is the result. So we defined 28 disease states. Each disease state is defined as the functional disability and its motor symptom score at the previous stages, and its changes and also aging. And we compare the actions, the clinician's action and AI's actions. So interestingly, from the 28 states, like 16, more than half of the actions agree each other. They are all just the same. But the remaining 12 different actions make a difference in lowering the motor symptom score. So we estimate the motor symptom score. We estimate the cumulative motor symptom score using the stepwise and weighted importance sampling. And then we repeat this process for 500 times for the bootstraps for making it more robust. And this is the result. So this one is for clinicians. And this is for the AI model. And this is just a baseline for zero drug, giving no drug at all, and this giving just random drug to the patient. This is simulation, yes. We didn't give random drug to the patient. So as you can see here, the AI model achieved a low level of the motor symptom score. And actually, clinicians achieve slightly not low as much as AI, but it's very consistent compared to the AI models. So here we think that the AI is actually explore a lot of action space, and it learns out of the clinician's practice, best clinician's practice. So that's why the AI model can achieve good performance compared to the clinician's model. So we think that we can complement each other. We can complete these AI models and clinician model each other, because AI model achieve a low level, and the clinicians can achieve very consistent level. So we'd like to combine those two as one system. So we think that the accuracy of reinforcement learning combined with the clinician consistency can complement each other, and we think that potentially allow a better outcome for the patient. And this is an interactive model. This is not a single time prediction. This is not a black box model. So the AI, the physician can look into the model, and they can see what's going on inside. So physicians can choose the suggest actions the AI model suggests, or they can just follow their action, their decisions. So this is more like interactive, so not a black box model. So we think that the reinforcement learning models cannot can't outperform the best physicians' actions. But we think that these models at least can help general neurologists or primary care physicians when they encounter some very complex cases, because like majority of the 32% of the PD patients actually see the primary care alone. So this is the end of my talks, and thank you for listening, and any questions?
So on your box plot slide, what did you mean by physician consistency? That seemed, unless I was misunderstanding it, to be the least consistent.
So
maybe?
actually for different...
Or you mean the spread of the interquartile range? I guess that's what you mean, right?
So this, so actually the Y value is a motor symptom score for each bootstraps. So for each 500 bootstraps, sometimes the clinicians, sometimes AI achieve very low level, but sometimes achieve very higher level. And clinicians actually achieve very consistent score for all 500 cases. We think that the clinicians, there's not much very big variance among in their performance. Yeah.
Have time for another question. But here, so what's more important in this application? Is it personalization?
I think it's kind of, I think the professional neurologists can outperform this one, can outperform the reinforcement learning. But for primary care, like for general practitioners, they might feel very difficulty when they have to consider like a lot of combinations of the patient's current status. In this case, we can support their decisions for the primary care physician.
So it's a cost reduction?
I think the decision support would be more good application in this case.